Today, we're going to look at heterocycles, cyclic molecules that have at least one heteroatom, or an atom that's not a carbon. And we're going to start off by looking at saturated heterocycles, those that lack any kind of pi bonding. And the first thing we're going to look at is their nomenclature. There's a lot of ways that heterocycles are named, and I'm going to show you what is really the most general and overall simplest form of systematic naming. So the first thing you need to do, of course, when naming anything is to find the parent chain. And for saturated heterocycles, the parent chain is simply the number of atoms in the actual ring, not carbon atoms, just atoms overall. So a 5-atom ring would be called a pentane or cyclopentane. We then place a prefix in front of the actual name to determine what heteroatom is present in the ring. We use aza for a nitrogen, oxa for an oxygen, and thia for a sulfur. The atoms of the ring are then numbered starting on the heteroatom. And yes, that means that your number one carbon of your parent chain actually will not be a carbon. It will actually be the heteroatom. So let's take a look at a few examples. And along the way, I'm going to show you some common names for some really important heterocyclic systems. So starting off with nitrogen heteroatoms. Here we've got a 3-membered ring with a nitrogen. So the 3-membered ring means that it's going to be a cyclopropane derivative, but we've replaced one of the carbons with a nitrogen, so we affix the aza prefix. So this is just aza cyclopropane. Aza cyclopropanes are fairly commonly encountered in synthetic chemistry, and they have a common name. They're called aziridines. They are basically the nitrogen analogs of epoxides. So in our next example, we've got a 5-membered ring. So this is going to be a cyclopentane, and again we have a nitrogen, so this is going to be an aza cyclopentane. And here I've introduced a substituent, a methyl group. And remember, we number this starting from the actual heteroatom. From there, we simply number consecutively going in the direction of the nearest substituent, so in this case, counterclockwise. That places the methyl on the 2 position, so we have 2-methyl aza cyclopentane. The aza cyclopentane system is actually really common in nature, and so it also has a really commonly encountered common name. They're called pyrrolidines. So our next example, we've got a 6-membered ring, again with a nitrogen. So this is going to be an aza cyclohexane. And in this case, I put a substituent, a methyl group, on the actual nitrogen. There's actually 2 ways you could handle this. Think about it. Numbering, we would actually number the nitrogen as atom number 1. So this could be 1-methyl aza cyclohexane. But it's an amine, which means you can also use the locant capitalized N. So this could also be called N-methyl aza cyclohexane. And as you might expect, the 6-membered ring being very stable, aza cyclohexanes are actually very common. And these are called piperidines. So next we've got a couple of examples of oxygen-containing heterocycles. First up, we've got a 3-atom ring containing an oxygen, so it's going to be a cyclopropane derivative with an oxa prefix, so oxa cyclopropane. Of course, you probably recognize these. These are also called epoxides or oxiranes. Another frequently encountered heterocyclic system that contains an oxygen is the Oxy Cyclobutane, a 4-atom ring with an oxygen. These are often referred to as oxytanes. And then finally, we have an example with a sulfur. So here we have a 3-atom ring with a sulfur, so we affix the thia prefix to a cyclopropane, and thus calling it thia cyclopropane. And again, this has a common name. Those 3-membered rings are pretty commonly encountered. These are called thioranes. Now, there are a lot more saturated heterocycles that have common names, but I chose these specific examples because they're so commonly encountered, both in synthetic chemistry but also in biochemistry. So typically after we talk about a new compound class and its nomenclature, we talk about how those compounds react. And if you think about it, what we have here is a variety of different kinds of compounds. The structures we just named represent amines and ethers and sulfides, all of which have very different reactivities. But the good news here is there's really not anything new to learn. Typically, heterocycles simply display the kind of chemistry that their parent functionality displays. So a cyclic amine is going to behave like an amine. It's going to do what amines do. So primary and secondary amines can act as nucleophiles. Amines have basic character associated with them as well. Cyclic ethers generally are pretty unreactive because ethers are quite unreactive, with the exception of epoxides because they can open up and relieve all that angle strain, that ring strain. So we're not going to cover anything new with respect to how these things react. They simply react in the way that their parent functionality reacts. So next, we're going to look at some unsaturated heterocycles, specifically aromatic heterocycles. Remember that aromaticity is a really powerful way of stabilizing a molecule through resonance. So we're going to break these down in terms of their ring size. So first, we're going to look at the 5-atom ring aromatic heterocycles, starting off with a nitrogen-containing ring called pyrrole. Note the two R's in the spelling. It's like pyrrole. Next, we've got a 5-atom ring aromatic system containing an oxygen, and this molecule is called furan. And then lastly, we've got a sulfur-containing 5-atom aromatic heterocycle, and this is called thiophene. Now, as you've probably guessed, these are all common names. These aromatic systems are rarely called by any kind of systematic name. I mean, if you think about it, the same was true for sort of the original aromatic molecule, benzene, right? Benzene, if you think about it, the IUPAC name would be 1,3,5-cyclohexatriene. But no one ever calls it that. We just call it benzene. Again, the atoms of the ring are numbered starting from the heteroatom. In case you have substituents, that's how you would number it. So chemically, how do these 5-atom heterocycles react? Well, again, these are aromatic molecules. And that means that they do the exact same kind of chemistry that benzene does. So again, there's nothing here really new to learn, or not much. The same kinds of reactions that we saw on benzene, those 5 EAS reactions of halogenation, nitration, sulfonation, and the two Friedel-Crafts reactions, all work on these 5-membered aromatic heterocycles. So, for example, we can take thiophene and apply to it the traditional halogenation conditions, chlorine and iron chloride. Now, we do have a Regio Selectivity issue here. With benzene, of course, being perfectly symmetric, all the carbon positions are the same. So removing any one hydrogen from benzene results in the same compound being produced no matter what reaction you're doing. With these heterocycles, we actually have two different positions where the substitution could occur. And again, if you think of the numbering, it's going to be on the second and the third positions. The Regio Selectivity of the reaction is that it prefers substitution at the 2 position over the 3 position. And this is simply because the intermediate form, the carbocation formed, has more extensive resonance stabilization when the second position is attacked versus the third position. It's essentially the same kind of an argument we made when we discussed the Regio Selectivity of substituted benzenes, the whole orthopara versus meta attack. One last thing I do want to mention is where do these ring systems fall in reactivity relative to benzene itself and amongst themselves? With respect to these EAS reactions, there is an order of reactivity. It turns out that pyrrole is the most reactive, followed by furan, and then thiophene, and then lastly benzene being the least reactive of all 4 of these aromatic compounds in an EAS reaction. Now, the reason we have this specific reactivity order is a little bit complicated, and unfortunately, it's not exactly a one-size-fits-all kind of an explanation. So let's tackle them kind of one by one. For example, pyrrole is more reactive than furan, simply because when you look at the resonance structures for the carbocation intermediate, you wind up with a positive charge on a nitrogen versus a positive charge on an oxygen in furan. And of course, oxygen being more electronegative than nitrogen, that's going to make that charge less stable on the oxygen than it is the nitrogen. And since the pyrrole has a more stable intermediate, it will have a more stable transition state and thus lead to a faster reaction. Now, comparing thiophene to furan, you might actually predict that the reactivity would be backwards from what I present here, because sulfur is less electronegative than oxygen. However, in this case, there's actually a second influence, and it has to do with the size of the sulfur atom versus the oxygen atom. Sulfur has third shell valence electrons, and oxygen has second shell valence electrons. However, each one of those atoms in these 2 molecules is bonded to carbon. And carbon is a second shell element, right? Its valence orbitals are in the second shell. When you look at the resonance structures where we have a pi bond between the heteroatom and an adjacent carbon, what we get in furan is the overlap between a p orbital on oxygen, that is a second shell p orbital, and a p orbital on carbon, which is also a second shell p orbital. In other words, those two p orbitals are the same size and they overlap very effectively. And remember, the better the overlap between orbitals, the better the bonding interaction. Compare that to the bonding we see in thiophene. Here, when we see that sulfur-carbon pi bond, that bond is formed between a p orbital in the third shell on sulfur and a p orbital in the second shell on carbon. And that third shell p orbital is much larger than the second shell p orbital on carbon. And because they're mismatched in size, they overlap very poorly, and that creates a very poor bonding interaction. Essentially, this means that the resonance contribution from the lone pair on the sulfur in thiophene to stabilize that carbocation intermediate is actually pretty poor. And it means that the intermediate formed from furan is simply more stable than that formed from thiophene, making furan more reactive. Now, the reason that all of these heterocyclic systems are more reactive than benzene itself is a little bit complicated. If you remember the frost circle method of describing the relative energies of all of the molecular orbitals, the pi molecular orbitals in an aromatic system, that's kind of how we explain why benzene is less reactive than all three of these 5-membered heterocycles. Essentially, the pi bonding molecular orbitals in these 3 5-atom heterocycles are simply of a higher energy than are the pi bonding molecular orbitals in benzene. And since they're higher in energy, that makes them more reactive. All right, we've got one more aromatic heterocyclic system to look at, and that is a 6-membered ring containing a nitrogen, and that is pyridine. Yep, good old stinky shrinky, which of course I call it that because pyridine smells horrible and essentially is known to cause testicular atrophy. So where are the sulfur and the oxygen containing 6-membered aromatic systems? Well, if you think about it, to make a 6-membered ring aromatic with an oxygen or a sulfur, because sulfur and oxygen are typically divalent, you'd wind up with a charged system, and it just really isn't stable. So pyridine is the only one we're going to talk about. Now, of course, pyridine looks an awful lot like benzene, and it is aromatic, and so it's going to do EAS reactions, just like the other heterocycles that we looked at that were aromatic. So here's an example of a halogenation with bromine and iron bromide. Again, we have a Regio Selectivity issue because there are actually 3 different positions that we can substitute a hydrogen for a bromine in this case. So pyridine typically likes to do EAS reactions at the 3 position, the other 2 positions being considerably less reactive. The reason for the selectivity at the 3 position again comes down to the resonance in the intermediates formed. When pyridine attacks at the 3 position, it avoids putting a positive charge on the nitrogen, whereas at the 2 and 4 position, you wind up with resonance structures that actually have a positive charge on that relatively electronegative nitrogen, making them less stable and therefore less likely to form. Now, overall, pyridine is actually less reactive in EAS chemistry than is benzene itself. And that often means you actually have to add a little extra energy in the form of heat to get these EAS reactions to work on pyridine. Now, one kind of chemistry that pyridine is actually really good at, or at least substituted pyridines, is a reaction you may have forgotten about, and that is aromatic nucleophilic substitution, or SNAR chemistry. If you recall, in an SNAR reaction, you have an aromatic molecule that has a leaving group attached to it, and a nucleophile can attack the carbon with the leaving group and go through kind of a bizarre nucleophilic substitution mechanism that eventually collapses and ejects off that leaving group. Now, SNAR chemistry on benzene requires not only the leaving group, but typically some kind of a powerful electron withdrawing substituent like a nitro group, either ortho or para to that leaving group. The presence of that electron withdrawing group enables the electron density to flow out of the ring and onto an oxygen atom where it's going to be more stable. Now, substituted pyridines don't actually need that electron withdrawing group. Pyridine is already electron deficient enough. So if you treat a substituted pyridine, so here we've got an example with a leaving group on the 2 position. Treat that with a nucleophile, and it'll displace that leaving group via the traditional SNAR mechanism. These reactions work best when the leaving group is either in the 2 or the 4 position. When you have a leaving group in those positions, the electrons can flow once the nucleophile attacks and put the negative charge on the nitrogen. And that can't happen when the leaving group is attached to the 3 carbon. So attack there is much, much slower. All right, we're going to wrap up our look at heterocycles by looking at some bicyclic aromatic heterocyclic molecules. These are simply molecules where we have a fused bicyclic system, where we have a benzene ring fused to one of our aromatic heterocyclic systems. So up first, we've got a benzene ring fused to a pyrrole. This is called indole. And the indole ring system is actually really commonly encountered in nature. For example, tryptophan and serotonin, molecules you may have heard of, both contain that indole system. Next, we've got a benzene ring fused with a furan, and this is called benzofuran. These aren't really nearly as common as the indole system, but it's still fairly common. And then lastly, we've got a benzene ring fused to a thiophene, and this is simply called benzothiophene. We can also fuse a benzene ring to a pyridine ring, and there are actually two ways this can be done, giving us two isomers. The first one is quinoline. Here we have the nitrogen of the pyridine ring bonded right next to the benzene itself. The quinoline substructure is pretty commonly encountered in nature. For example, quinine. This is a molecule found from a cinchona tree, and it's been historically used to treat malaria. In fact, if you've ever enjoyed a gin and tonic, the tonic water actually contains a small amount of quinine. In fact, that's how the gin and tonic was created. It was a way of administering a really foul-tasting medicine in a more pleasurable kind of a way. A derivative of quinine, which is chloroquine, also has that quinoline subsystem, and this is being used as a possible treatment for COVID-19. Now, the other way you can fuse together a benzene and a pyridine places the nitrogen kind of adjacent to the carbon next to the benzene. And this is just an isomer of quinoline called isoquinoline. It's not nearly as commonly encountered in nature, but it is still prevalent. Now, because these bicyclic molecules are aromatic, again, they're going to do simple aromatic chemistry like EAS reactions. So let me show you a couple of examples, because there are some really big Regio Selectivity issues that we have to talk about. So if we were to take something like indole and attempt a halogenation on it, there are 6 possible hydrogens attached to carbon that could be replaced. That could lead to 6 possible Regio isomers as products. But we can attack this logically. We have here 2 aromatic rings fused together. We have a benzene and a pyrrole. And we know that pyrrole is more reactive than benzene in an EAS reaction. And that means that the pyrrole ring is going to be the one that actually acts as the nucleophile and not the benzene. And that limits us down to simply 2 positions for attack. We also know that pyrrole prefers to react in an EAS reaction at the 2 position. And so when we combine those 2 pieces of information, that pyrrole is more reactive than benzene, and that pyrrole prefers to react at the 2 position, we know exactly where the halogen is going to go in our product. It's going to go on the 2 position of the more reactive pyrrole ring. So here's another example using quinoline. Here we'll do a sulfonation. In this case, what we have in quinoline is a benzene fused together with a pyridine. And in this case, benzene is actually the more reactive of the 2 rings in an EAS reaction. That means that the benzene is going to act as the nucleophile, but that still gives us 4 potential sites for reaction, right? There's 4 hydrogens attached to the carbons of the benzene ring. Now, experimentally, it's been found that the EAS reactions on quinoline prefer to place these new substituents on the carbons that are closest to the pyridine ring. And the reasons for that are really beyond the scope of this course. But no, we were still able to limit the overall Regio selectivity, right? You think about it, in the original quinoline molecule, there were 7 hydrogens that could have been replaced, and we were able to remove 3 of those from the possibility, right? We know that the carbons on the pyridine ring, that pyridine ring is less reactive. Those are less likely to get substituted. The benzene being more reactive in an EAS reaction, it's going to be one of those sites that serves as the nucleophile. All right, that's going to wrap up our brief look at heterocyclic chemistry. We've really only just barely scratched the surface here. For example, we haven't talked at all about what happens when you have multiple heteroatoms in a ring, and those types of systems are actually quite common. But again, recognize there's not a whole lot of anything new here. We've got a handful of new names, but the actual chemistry involved, the reactions, are simply old reactions. Your saturated heterocyclic systems just do whatever the parent functionality does. Amines act like amines. Ethers act like ethers. And then with these aromatic molecules, again, they're aromatic. They do aromatic reactions like EAS reactions. We simply have to worry about the Regio selectivity and the general reactivity order of these aromatic compounds.